Okay. Today we're talking about regression lines. And regression lines model the relationship between two variables. Yeah? Specifically two variables that when we plot them on a scatter plot, they look roughly linear. Yeah? They don't look linear. Why would we be fitting them with a line? We'd fit them with something else. You guys know what lines look like. What was the very first form of a linear equation that you guys ever saw? Y equals mx plus b, right? Slope-intercept form. Very first line that you see. Statisticians like to be different. So we are actually going to use y hat equals a plus bx. It is y hat, y with his little hat on, because we want to distinguish it from the data value y. Y hat is not a data value that came from an actual living, breathing human or a member of my sample. It is my predicted y value. So I now have two y values. I have the actual y value that came from a member of my sample. I have the predicted y value that came from my linear model. And if my model is a good model, those two numbers should be close together. My model is a bad model, those two numbers are far apart. Yeah. So you'll notice that that equation is backwards from the order we write our typical polynomials in. Yeah, we like to put the x's in front. There are two things that are still true about our y hat equation. The first is that the slope is still the coefficient on the x term. The slope is the thing being multiplied by x. Yeah. The other thing that's still true is that the y-intercept is still the constant term. So looking at our equation, y hat equals a plus bx, which of those two letters, a or b, is the coefficient on the x? Raise your hand if you know. I see Jacob and Drew. You can do it at the same time. Give me the letter. Is that what you were going to say? We got a B. I am inclined to agree. Yeah. B is the slope. Is this the thing being multiplied by x? It's the coefficient on the x, which means A is my constant term, my y-intercept. That is upsetting, because up to now in all of your other math classes, we use B for the y-intercept and another letter for the slope. Here, B represents slope, not y-intercept. It is going to be confusing. I am sorry. I am not the person who decided to write it that way. You will notice when you run lin-reg like we did last week for our correlation coefficient, there's two lin-reg functions for a reason. Some statisticians are reasonable human beings, and they use traditional slope-intercept form to write their linear models, y equals ax plus b, where b is y-intercept. Unfortunately, the AP board is crusty and outdated, and so they do y hat equals a plus bx to be difficult. So option 4 does not exist for you. Use option 8. I am sorry. The reason we go through the trouble of writing these models is the same reason we do most of inferential statistics. I want to make predictions. In this case, I want to predict the value of a response variable given a value of input for my explanatory variable. For our graphs earlier this week, if I know a student's height, I want to be able to predict the max time they can hold their breath. Right? That's the idea. So we're going to do an example where we use a linear model to make some predictions. My hope is that this feels familiar because this is a skill that you should have seen in Math 1. And I know that because I taught some of you Math 1. So I need someone with a nice loud voice to read just the example text above the graph. Who's got a nice loud voice? I'm going to let Yari do it because you've already answered a question, but thank you for the enthusiasm.
Property taxes in Pennsylvania, the state assigns a value to each house called the assessed value. The scatter plot shows the relationship between y equals assessed value of a house in dollars and x equals living space in square feet. For example, for a sample of houses in Pittsburgh, the regression line y equals 105, 640, 34 plus 36. 0.02R has been added to the scatter plot.
Very good. Thank you, Yari. That's perfect. Very good. So we have a graph, living space versus assessed price, and the line is our predictive model. That's our regression line, and the dots are the raw data that we collected from that sample of houses. Yeah. And the first question says, a new house with 3,000 square feet of living space is being built in the neighborhood. Predict the assessed value of this house. So I see two quantities mentioned. I see 3,000 square feet, and I see predict the assessed value. I need to know which of those is an X value, an input value, which of those is a Y value or an output value. So let's start picking on some people. Amy, is that 3,000 square feet an X value or a Y value? Amy says an X value. How do you know? I'm inclined to agree. How do you know? But how do you know it's the explanatory? The graph. The graph. Look at where that shows up. Yeah. I can see areas plotted on the x-axis. Must be my input, must be my explanatory. Good. So they've given me an x value. They want me to predict a y value. And we have an equation that relates the two. I'm going to give you about 60 seconds. I want you to talk to your neighbor. Given that x value, how am I going to make a prediction for my y value? Honey, what am I going to do with the formula? Okay, how does that help us? Perfect. I'm going to take that x away and substitute in the value they gave us for x. Perfect. Very good. Yay. And that's going to give us, I should label this part A. And I think I did this on my calculator earlier today. I did, and I got 2,000, 1,300, 734 cents. And I get thumbs up. Very good. This is in dollars, because this is an assessed value. The y-axis is labeled in money. So for a 3,000 square foot house, the assessed value of the house is a little over $200,000. Clearly, this is not in California. Not so bad. Something we've done in math class before, yeah? You'll notice B, very similar. Predict the assessed value of a house with 2,256 square feet of living space that is for sale in this neighborhood. So I'm going to give you just a minute in your small groups. I want you to do B, and then I'm going to have somebody come up the board and do it for us. This is the quietest you've been all year long. A warning, I called Jaden's name. Jaden, can you walk me through how to do this? Jade, what should I do first? Did I do that correctly? I see you nodding. Very good. Did you do that on your calculator? What did you get? What came after the 186? 911? 01. 01. 2. Did anybody else get that? Just the cents were different. So that was probably a typo somewhere on the calculator. Yeah. Good. Very good. Yay. So I have a deep thought question for you now, because this is AP stats, not just regular stats. And the question is, how confident are you in your predictions? Remember, 2 separate predictions, 2 separate inputs. I'm going to give you about 90 seconds in your small group. Talk to your neighbors about how confident you feel in those predictions and why. You doing okay? Is this trash? Oh, this is from my pre-calc class. Shame on them.
Yeah, I don't know where that came from.
That came from my pre-calc class too. They were a very trashy class today, apparently. I mean, yeah. If you don't believe in ghosts, that's a good deal. Heck, even if you do believe in ghosts in California, that might be a good deal. I know, but I already called on you today. Yari, what did your table discuss? How are we feeling in terms of confidence in those predictions?
Well, for me at least, I said that I'm pretty confident in now answering, well, like, trying to find the answer to put it down of like what's expected and how to put it in calculated statements to like answer it.
So you're very confident in yourself and your ability to make the predictions, which is good. How do you feel in terms of the accuracy of those predictions we made together? Good, bad?
The confidence comes from the calculator. Like if I learn about it.
Okay. Okay. Did anybody else get something else? I'm going to do Ashana and then Drew, since you guys both raised your hands. Ashana, what are you thinking?
I was telling Bailey that I do see like an increase in price based on like an increase in square footage, but I feel like the price could be a couple dollars off just because this is a prediction, so it's not like inaccurate. It's just kind of like an estimation, or like how Bailey said, like an educated guess or prediction.
So those answers match the pattern that you see here, but there's
I feel like there can still be a couple like outliers. Or
variability. There's some variability there. Okay, good. Drew, what about you?
I still find confidence around like the predictions given are like man, not good, not bad, since the graph seems to be like a moderate or weak association.
So we expect as area goes up, price goes up, but we also expect this data is not a super strong linear, and so we might be off a little bit. Is that kind of the vibe I'm getting from the class? Okay, then I have another question for you, which is, are we equally confident in our prediction for A versus our prediction for B? Give me a thumbs up if you think you are, a thumbs down if you are not equally confident in both of those. And I see a mix of both. And I'm going to start with the thumb down, thumb sideways tables. What are we thinking over here? Ivan?
So I said just because A, I feel less confident in because it's farther away from the hard data. So it's not that majority, like major problem. I would be confident, but it's just like a slight unconfident.
Does that kind of match what you were thinking, Jacob? Yeah? I made that note too. I agree with everything we wrote in there in red together. For all of our predictions, this is not a super tight fit. So there's some variability. I expect my predictions are not going to be spot on. I think our prediction for B is more likely to be correct than our prediction for A. Because B was evaluated for 2,256. 2,256 is right about here on the x-axis. I have some data in and around that x value. I actually collected data points around that area. And so that linear model is going to accurately reflect that range of x values in that region. I did not collect any data much past 2400, 2450, because there isn't anything in the graph bigger than that. 3000 is outside that range of data I collected. And so my output is less likely to be accurate. And that idea is called extrapolation. Extrapolation is when we take a model and we use it for prediction for x values outside of the original range of x values. And as a general rule, statisticians would caution you to not do extrapolation. And here is why. When we create models, we are creating models with a very limited domain, small range of x values. And it is entirely possible that the section of graph that I'm looking at that looks normal, when I get outside of that domain, starts to do this. Cubics, sometimes in the middle, look a little linear. Yeah? Exponentials, if I zoom in on certain parts of that exponential, like a tiny little area, that's going to look linear. Quadratics, if I zoom in on a tiny little area, is going to look linear. There are lots of curvilinear functions that if I limit myself to a tiny range, behave like they're linear when they're not. And if my data matches one of those patterns, and I built a linear model for it outside of that range of input values, I'm going to get really, really bad answers because I treated my data as linear. The further I get from my original data, the worse that estimation is going to be. So really, really dangerous to use your linear model for data that is way outside of your original input. Yeah. Close to the edges is kind of okay, but way outside of it, not trustworthy. Okay. Questions? No. You all look dead inside because it's Friday. You made it. You made an e-hall pass and everything. Good job. Yes. What? Huh? What? All right. On that idea of our model being a good predictor of our output or not is the idea of residuals. Residuals. And residuals measure the difference between our actual y values and our predicted y values. And we expect there to be a difference because we know that there is some variation in our actual y values. And I can see I made a typo there when I wrote this. Actual y values. And we can see residual is actual y value minus predicted y value. Notice that it's only looking at the y. It is a vertical distance. Yeah? I'm looking at the vertical difference between the output for the input and then the predicted output for the input. It is important that you remember actual minus predicted, because this is one of those things that is not on the equation sheet. Yeah? The good news, when you run linreg on your calculator and you find your correlation coefficient, it does this in the background in memory. So anytime you run linreg on a set of paired data, it has the residuals stored in a resid list somewhere in its memory. Meaning you can access those residuals anytime you run linreg, which is great. All right, so we're going to do an example to look at how to calculate and interpret a residual. Yeah. So somebody who hasn't spoken yet today with a nice loud voice, who wants to read our example? Nobody's volunteering. Sophia, would you please read our example?
18 centimeters. The regression line is y hat equals 95.78 plus 0.026x. Find and interpret the residual for the student with a body temperature of 97 Fahrenheit and a heart rate of 78.
Very good. And you notice that that should be 78.0 because 780 beats per minute, that is a heart exploding in someone's chest. Humans do not beat that fast. So I made 2 typos on this page. I'm sorry. All right, I see 2 things that I am given. I am clearly given a linear model. Y hat equals 95.78 plus 0.02x. I am also given a data point. I am given an x value and a y value. I am not told which one is which. Temp of 98, heart rate of 78. Question is, which one is which? Valeria. Which of those 2 quantities is plotted on the x-axis? You can't see the board, you can see it on your paper. What's on the x-axis? Heart rate, yeah. So heart rate is our input. So I'm going to copy the 78 first, 78 BPM. Temperature must be my y. They gave us the data point 78,97. And the directions say find and interpret the residual for that student. Right now I have x and y. What do I need that I am currently missing in order to calculate my residual? Y hat, very good. We got to use our predictive skills. First thing I'm going to do is figure out y hat for this student. And you guys told me, use the equation, plug in the value you were given for x. X is 78. And when I did this earlier, I got that my y hat is 97.81 rounded. It's like 97.808, I think. I see nodding. Yeah. 97.81 what? Oranges? Dollars? Fahrenheit. There we go. Good. Input BPMs, output temperature. Perfect. So we now know the actual temp of that student was 97. The predicted temperature was 97.81. So we were close, but we were a little off. To figure out how off, we're going to calculate the residual. So resid equals y minus y hat, which is 97 minus 97.81. I can do that in my head, negative 0.81. I see some nodding. That's good. That residual tells me 2 things. First, based on the fact that the residual is negative, is my data value above the line or below the line? Below. Very good. So I know that my data value, that 97, is below the line. The next thing we need to consider is whether that difference is big or small. Good predictive models will result in small residuals. So I'd like to see that as a small number. Is 0.81 of a degree a small change in temperature? The answer in reality is yes, because Fahrenheit degrees themselves are tiny units. We've got less than 1 of them. That's a tiny change in temp. So our model did a pretty good job of predicting this student's temperature, but it overestimated it just a little bit. She was a little bit cooler than the model predicted. Very good. The reason that we are interested in residuals is, like I said, a good model should minimize them. We want to make them all as small as possible. And that process is called regression. We're going to talk more about that on Monday. What I would like to do for the last part of class is practice interpreting some of the numbers that we are seeing. Yeah. Okay. So we'll start with interpreting slope and y-intercept. This is stuff you probably already know how to do. We're just taking it now and putting it in the content area of stats. Wow, words are hard. Oh, my poor little brain. No pity on your faces at all. All right, so regression equation, y hat equals a plus bx. A is our y-intercept. In previous math classes, what does the y-intercept measure? Raise your hand if you remember. I know some of you should remember because I taught you math 1. What is the y-intercept in a graph? Louder? Not input. Good guess, but not input. Yes, Austin. So can you be more specific? What value when what is 0? When x is 0. Very good. So this is the y hat value when x equals 0. So this is the predicted output when we have an input of 0. For example, looking at that graph of square footage versus assessed value, this would be the predicted assessed price for a house that had no square footage. And regardless of what you get out of that, it's nonsense because a house that has no square footage is not a house. Can't be worth anything. So sometimes our y-intercepts will have no practical interpretation in the real world, and you'll be expected to explain that when they ask you about it. Okay, now for the other one, slope. What is slope? Raise your hand if you remember. Everybody's hands are broken today, preferably somebody who hasn't spoken. Yes, Jaden. Measures the tilt of the line. Good. I agree. Slope is a measure of tilt. Can somebody give me some more mathy vocabulary to go along with that visual image? Yes. Ooh, very good. So this is the change in y hat for every 1 unit increase in x. Also known as rise over run, or the tilt of the line. All of those definitions are correct. This one is going to help us in terms of connecting that number slope to what's happening in the real world with it. Because unlike Math 1, we are now very concerned with what our numbers mean in context of the real world. We're going to do an example where we get to practice these skills. So we're going back to our regression line that's modeling the relationship between body temperature and heart rate for a sample of 18 teenagers. It says y hat is 95.78 plus 0.026x. It says interpret the slope of the regression line, which means I have to know what the slope is. Nancy, in that equation, can you tell us which of those two numbers is our slope? Tempting. It's the first one we see. Which one is the coefficient on the x? Which one's being multiplied by x? 0.026, yeah. So slope's the teeny one in front of the x. Good. And we have to interpret what that means. And we're going to use the definition for slope as our sentence frame. Yeah? I'm going to do it backwards. I'm going to start here first, and then I'm going to go backwards. So for every unit change in x, what happens to y? Yeah? So for every one, and then I have to think, we had body temperature and heart rate. Which one of those was X and which one of those was Y? Heart rate was our X, good. Body temp was our Y. So for every 1 BPM increase in heart rate, which is our X, we expect a, and then I have to make statements about the slope. I need to know the number and I need to know the sign. Is the slope positive or negative? Positive means my line is increasing. So as X increases, I expect an increase of 0.026. And then what is Y measuring? Temperature in Fahrenheit. For every 1 BPM that heart rate goes up, I expect the body temp to increase by 0.06 degrees Fahrenheit. So as the heart rate goes up by 1, the temp goes up by a little bit. Yeah. Not so bad. Not so bad. We can do this. All right, so the next one, a little bit weirder, asks us, does the value of the y-intercept have meaning in this context? If so, interpret it. If not, explain. So, Samuel, what is our y-intercept? I agree. So y is 95.78 degrees Fahrenheit, which represents on my graph the 0.0 BPM, 75.78 or 95.78 degrees. The question is that a reasonable value in the real world? What does 0 BPM represent? Flatline. This is a student who is no longer alive. Just a little depressing and a little morbid for a Friday afternoon, yeah? So we have two choices here in how we write our answer. We could state this is the expected body temp for somebody whose heart has just stopped. That is accurate. That is what that point would represent in the real world. Or we could say that it's nonsense because we know that when you die and your heart is no longer beating, your temperature drops and it's not going to stay at 95.7 degrees Fahrenheit. Either of those explanations is fine. Yeah. What the AP board is looking for here is that you understand that that number should be couched in context from the real world, and you need to be able to make sense of whether that is reasonable or not. For example, if we go back to our housing situation, if I got an intercept of negative $2,000 for a house of 0 square feet, is that a reasonable value? No, because that's basically somebody giving me $2,000 for no house. One, the house doesn't exist, and two, nobody gives away $2,000 for funsies. So that would be a nonsense value, and I would need to tell them that it is nonsense and why I know that it's nonsense. Yeah? More often than not, that y-intercept is going to be nonsense, because more often than not, we're looking at data that is far from 0. In our case, we were really far from 0. We were looking at BPMs up in the 60s, 70s, 80s. So that probably isn't accurate to begin with because 0 is way outside of our data range. Good. Yay. Very good. Okay. Questions? No. All right. Let me preview here. When I see you next time, we're going to talk about how to find those models, those least squares regression line equations. Your calculator can do it for you. You already know how to do it, even though we didn't talk about it. I'm going to show you how to do it by hand, which is good for you. While we're doing that, I can also show you how to find the correlation coefficient by hand. For now, just use your calculator. You have a little bit of class time to work on your homework. Yeah? No, it's good for you. 2B is due on Monday. Activity, are we compatible, is due on Monday. If you have time, start 2C. Some people did, not everybody has. Yeah. And a lot of people do. I have them in my green to grade box for this weekend. Yeah.